Okay, thank you. Thank you everyone, and especially to the organizers for inviting me and my collaborators to speak here. I would also like to thank the Simon's collaboration on UQM. I've really learned a lot from talking to the participants in the conferences and seminars run by the collaboration. So as the title suggests, this is going to be a continuation of Nati and Hota's talk. And it will be based on the series of paper I wrote with Nati, Pranay, Hota, and Tom. But particularly, I will be focusing on the latest paper here. I hope everyone can see my cursor here. All right.
I don't think I can see your cursor. Sorry.
Oh, you don't? Okay.
Oh, wait, no, I can see it. Sorry. Continue.
Okay, great. All right. So I will follow the same organization as in Hota's talk. I will start with a warm-up example where everyone is familiar with. That's the 1 + 1D XY model, more precisely the two-dimensional Euclidean XY model that has already featured in Oshikawa's talk. The action is given by this, where the sum is over all the lengths on the two-dimensional Euclidean lattice. And there's a cosine interaction of nearest neighbors, degrees of freedom. As Hota already reviewed, this XY model on the lattice has an exact U1 momentum symmetry, where the term momentum here refers to the target space. And this is the terminology commonly used in high energy physics. In any case, there is an exact U1 global symmetry that shifts the circle value variable phi by a constant. On the lattice, that's the only U1 global symmetry. In the continuum, however, namely the C = 1 compact boson CFT, there's an additional U1 global symmetry that emerges in the low energy, and that's the U1 winding symmetry discussed by Hota. And the question asked by Hota at the end of his talk is that can we have this winding symmetry on the lattice as well? Not necessarily the same lattice model, but perhaps some deformation of the original lattice model. All right, so can we do that? There are several difficulties in realizing the winding symmetry on the lattice. First, the winding symmetry in the continuum measures how many times the field phi wraps around as you go along a circle in space. And it really relies on the continuity of the fields. But there's no sense of continuity of the fields on the lattice, and hence naively, there's no winding symmetry. Second, in the continuum, there's a mixed anomaly between the U1 momentum and the U1 winding symmetries, and it's not easy to realize this mixed T-Hoof anomaly on the lattice. This comment has also been made in Mong's talk. And since there's no winding symmetry, there's no exact self-duality on the lattice. Relatedly, the lattice model has a BKT transition between the two faces. So in order to realize such a winding symmetry on the lattice, our strategy will be to suppress the vortices on the lattice. This is an old strategy that has been used by many people in the literature, and we will generalize these ideas to arrive at the new lattice model. To start with, we follow Illain's approach to the XY model by considering the following action. So this action differs from the previous one in that now it's quadratic in the field. We replace the cosine by a quadratic term of delta phi, but the price we pay is that we introduce an integer gauge field and mu here. And phi here started its life as a real value field. This mu is an integer gauge field living on the link, and there's an integer gauge symmetry that acts on the real value field phi and the integer value gauge fields in the following way, where this little k is the integer gauge parameter. The integer gauge symmetry effectively makes the phi a circle value field. On this slide, this is just the ordinary standard Illain approach to the XY model. When the coupling here is very large, this gives a good approximation of the original XY model. Next, we would like to suppress the vortices of the XY model, or its illain version, by adding the following gauge invariant term. The thing in the parentheses is the field strength of the integer illain gauge field. And we add such a term with a large kappa to suppress the field strength. This will do the job of suppressing the vortices. As we take the coupling kappa to infinity, the illain integer gauge fields becomes flat, and we can enforce this limit by replacing the action by what we call the modified illain action. It differs from the illain action by this second term, where we have introduced a Lagrange multiplier field phi tilde. If we integrate out the Lagrange multiplier field phi tilde, that enforces the flatness conditions of the illain integer gauge field. Let me emphasize that this modified illain action is a lattice action of compact scalar fields. Both phi and phi tilde are compact. Phi started its life as a real value field, but there's an integer gauge symmetry making it effectively compact. Phi tilde was introduced as a Lagrange multiplier, but since it's multiplied by an integer quantity, it has a 2-pi periodicity. And we cannot rescale the periodicity arbitrarily. This is really a lattice model of compact fields instead of non-compact fields. All right, so what's the novelty of this modified illain action? This lattice model has both an exact momentum U1 symmetry, which was already there in the original XY model, but also an exact winding symmetry. The momentum U1 symmetry just shifts the phi variable by a constant. The novelty is that there's also an exact winding symmetry that shifts the Lagrange multiplier field phi tilde by a constant. These are their corresponding Noether current on the lattice. Since the lattice model has both U1 symmetries, it realizes the mixed 't-Hooft anomaly in the same way as in the continuum discussion. It's interesting that this modified illain action exhibits 't-Hooft anomalies between two U1 symmetries that act locally on the variables. The reason that there could be such a 't-Hooft anomaly is related to the fact that the local Lagrangian density, namely the summand here, or even its exponentiation, are not invariant under the U1 cross U1 tilde symmetry. As you can see, if you shift phi tilde by a constant, it doesn't leave the summand here invariant, but only the after you sum over all the plaquette, the exponential to the action will be invariant. The mixed 't-Hooft anomaly between the two U1 on the lattice implies that the low energy phase of this lattice model, if we impose both U1 symmetries, are gapless for all values of R. This is because a gap phase cannot possibly reproduce or match the mixed 't-Hooft anomaly between two U1 global symmetry. Hence, this new modified illain lattice model has no BKT transition, in contrast to the original XY model. Furthermore, we can apply the Poisson resummation formula on the integer gauge fields and mu here, and rewrite the modified illain action in a different way. After a few lines of algebra, you realize that after applying the Poisson resummation, it gives back the modified illain action, but exchanging phi with phi tilde, and also exchanging the radius with 1/2R. This realizes the self-duality, namely the T-duality, that was already there in the continuum. The self-duality exchanges the U1 momentum and the U1 winding symmetry. Okay, let me give a similar table as in Hota's talk. We started with the original ordinary 1+1D XY model. It's an interacting lattice model that has a single U1 symmetry. Therefore, there's no anomaly and no exact duality on the lattice. On the right column, we have the C=1 continuum CFT discussed by Hota, and also the new modified illain lattice model. Both of them are free, namely quadratic. Both of them have two U1 global symmetries. Both of them realize the mixed Hoof anomaly, and both of them exhibit the exact self-duality. That concludes the warm-up part of my talk. And then we can move on to the more interesting model, the 2+1D XY-plaquette model that was already introduced in Lattice talk and also by many other people in this conference. So we are now in one dimension higher. We have a Euclidean time direction with the nearest neighbor interaction in the Euclidean time direction. And in the spatial direction, we now have this plaquette interaction, and we sum over all the XY plaquettes. Again, we apply the Villain formalism by replacing the cosine by the quadratic action at the price of introducing integer gauge fields n tau and nxy with the following integer tensor gauge transformation. N tau and nxy are the 2+1 dimensional integer version of the tensor gauge fields in Shu and Wu's paper back in 2008. Next, we would like to suppress the vortices by adding the field strength square term to the action. As we take the suppression coupling to infinity, we can replace the action by the following modified Villain action. It differs from the original Villain action by the second term, where we have introduced a Lagrange multiplier to enforce the flatness condition of the Villain integer gauge field, and that's equivalent to completely suppress the vortices. Again, this is a lattice model of two compact scalar fields. Similar to the 1+1D XY model, the modified Villain lattice model here is very similar to the continuum field theory. In particular, it realized the exact U1 momentum symmetry, the exact U1 momentum subsistence symmetry, and the U1 winding subsistence symmetry. The U1 momentum subsistence symmetry acts on the fields by shifting it by a function of x plus a function of y. That's why it's a subsistence symmetry. And similarly, the U1 winding symmetry acts on the Lagrange multiplier field phi tilde. It realizes a mixed Hoof anomaly between the two U1 subsistence symmetries on the lattice. Again, we can use the Poisson resummation to show the exact self-duality on the lattice, which exchanges phi with phi tilde and exchanges the temporal lattice coupling with the spatial lattice coupling. So we again have this table where on the left is the original 2+1D XY plaquette model, first introduced by Perelman-Conti, Valens, and Fisher. It's an interacting lattice model that has a single U1 subsistence symmetry. There's no anomaly on the lattice. There's no exact self-duality. On the right, we have the continuum phi theory that was also introduced in Perelman-Conti et al.'s paper and later analyzed by many other people. In this most recent work with Nati, Pranay, Hotat, we introduced a new modified Villain lattice model that shares many similar features as the continuum field theory. Both of them are free. Both of them realize two U1 subsistence symmetries, and the two U1 subsistence symmetry has a mixed Hoof anomaly, and they exhibit exact self, and the model exhibit exact self-duality. So in this talk, I have discussed the modified Villain action for the ordinary XY model and for the 2+1D XY plaquette model. In our paper, we have also analyzed the modified Villain action for various other standard lattice models. This includes the XY models in diverse dimensions and the standard U1 and Zn gauge theory in diverse dimensions. We also apply the same strategy to the more exotic model, such as this includes various gapless and gap fractal model, and such as the famous X-cube model. The modified Villain lattice models for this exotic system make rigorous our treatment for the discontinuous fields that we encounter in the continuum field theory. Furthermore, they are very close to the continuum field theory in that it exhibits emergent global symmetries, to Hoof anomalies, and exact self-dualities. All right, I'll end my talk here and thank you, everyone.
Great, thanks.